So I have an interesting job here I wanted to show y'all. And we're doing radiant heat with PEX pipe in the floor, 2 inches of foam insulation underneath the cement. And then we're doing air cooled. I got the little air handler starting to go in up there. And it's heat pump because we don't have natural gas out here. We're gonna put the heat into the floor through this little setup here. Got our heat exchanger, refrigerant to water. These were 3.5 ton, so I'm just gonna put 2 of them together for 7 ton. Here's all our PEX. So this is all the heater pipe. Here's our water reservoir, bulkhead fittings. I went with a flat one because you get a nice seal with the bulkhead fittings. So basically the way the system works is our heat pump is going to make our water hot, and we're doing counterflow. You always want to do counterflow. So we're doing counterflow for heating. We're not going to do cooling with this except defrost for a few minutes. So our hot gas is coming in on this side, and it's going to be touching the hot outlet. So that way the hottest gas is touching the hottest water. The coldest gas is touching the coldest water. I'm putting a couple safeties here because the customer is actually going to be doing a switchover by pumping down, isolating either the heat pump or isolating the air handler. And so they can use the same condenser unit and in the summertime versus the winter. And with 4 isolation valves, I'll show you those, I have to install those. But basically it's just you pumping it down, valve off, and then you can run the other circuit. But you have to do some safeties to make it foolproof. So I'm doing a freeze thermostat, which is right here. That way, if this for some reason went to cooling, we're not gonna freeze and bust it all up. And also doing a flow, basically a flow switch. Also, since we're having isolation valves, there's always the potential the customer could screw it up and not pump it down into the condenser, and then say pump all the refrigerant into the barrel, and then the barrel heats up, and then you end up blowing something up. Put some 600 psi pressure reliefs. So that makes it pretty foolproof, where if it's not pumped down properly and then it's left to get warm, it'll just pop a relief valve. And of course there's peanut safeties, high pressure safeties. So the pressure relief should never pop. You leave the cap on there to tell if it did pop, because it'll blow the cap off. And you can see I built a table. Got myself a little pan. So if we got any water leaks, right there. The system's really simple. The pump is right here. It's just gonna come on, I got the relay, it just come on with the green wire, just like a fan. So when the thermostat calls for green, turn on the pump. The interlock will make sure the compressor only runs when the heat exchanger has water. And so the interlock breaks the Y. And that's it, and just runs like a normal heat pump. It'll do its defrost, so it'll run, in cooling mode. Using PEX for the water connections, 1 inch, and pretty simple. Draw water off the bottom of the tank, go straight into the pump. I'll have a strainer inside the tank. This tank's kind of nice, I can reach my arm in there. Get a strainer, then out of the pump, just zoom around here to the heat exchanger. And the heat exchanger, I got them piped in parallel on the water. That way I want to have maximum water flow. Then the heat exchanger goes out to our supply manifold, we got our safety switch there, flow switch, and then the return, it's gonna dump back into the tank. And I raised this up a little bit, so if the tank's ever low, you start hearing it splash in there, and then you know you gotta juice the loop with some water, which was, you know, basically just pour in a bucket. And then we got plenty of room for expansion. And I checked on radiant floor cooling. It doesn't really work because your floor ends up just sweating, and you know, who wants that in the summertime? So that's why we're gonna do air for the cooling. You can see in here, significant amount of condensate got into the line. You can see that. Because the line was cold outside and is drawing in moisture and condensating. So I'll have to do a good triple evacuation on this one, get all that moisture out. 5% silver solder, low temperature. It's called Stay Bright. I used Stay Bright solder, keep the valves cool. You can see we got piped in. We also got, so the oil is not going to collect. That's why I got a little bit of slope there. So the circuit that's off is not going to collect any oil right there on the pipe. Liquid's not so much of an issue. Go ahead and insulate and wire it up now. I love this UV wrap. It's basically packing tape. You wrap it around your insulation. This stuff lasts forever. Here's the third vacuum. You can see about 150 microns. I use a vacuum manifold with 3/8 hoses. So if it's 150 microns here, it's probably 300 microns right there. I had to raise the tank up here to get the pump to self-prime. Also mounted the pump sideways. It primed a lot easier. And to prime it, you cycle the power a couple times. It lets the bubbles come back. So we got a good flow. Add up all the flow gauges. We're doing about 8.5 gallons per minute. You can see there's no flow. Turn the flow back on. And then here I want to show what it sounds like when you're low on water and you have to juice the loop. So our water level is right below our return line. And as you can hear, get the little splashing sound. Here you can see the radiant floor. Pipes are starting to show very nicely. I did find an issue here on the heat exchanger. The way I did it, I did parallel on the water and then series on the refrigerant, and you end up, the top heat exchanger is doing all the heating and the bottom heat exchanger is basically just holding liquid refrigerant, doing nothing. And you can see it on your temperatures. I'm getting 4.25 tons out of a 5-ton, and it's about 25 degrees outside. But I run up, the head pressure runs up on a defrost, and I actually ended up hitting the 500-pound pressure shutdown. And because what happens is that this thing is already over half full of liquid, and then when it switches to cooling, the expansion valve feeds more because the bulb, is hot. and it ends up going 100% full of liquid. And then the expansion valve starts pinching back, but it only pinches back to 3/4 full of liquid. So we end up with too much liquid. So I'm repiping here. It's important that the flow is equal. So on hot gas, I'm not concerned about liquid. So these can be vertical. If this were the liquid line, all your liquid would go on the bottom circuit and gas in the top, which would be bad. So on the liquid line, I'm doing them vertical, and ideally you'd have a distributor, but they don't make a 2-circuit distributor because this is a 2-circuit system. So I'm going to make a distributor here. There's a lookup table for what size you want your feed capillaries to be. 5/16 rates at 2.5 tons. Is you want a 2-pound drop on your feed capillaries to also ensure equal feed on both coils, and also large enough to handle the reverse cycle heat pump. So on these we're going to do 5/16 going in vertical, and a similar setup like this, which I just made out of a cap. You can see there. Now all this slag would be on the inside of the pipe, so it's important to have CO2 inside the pipes when you solder, so the pipes stay nice and shiny. Finish the repiping, so you can see the outlet or the inlet on the heat cycle, inlet on the cooling cycle, and made sure that the pipes are exact same height there. Chart shows 5/16 for 2.5 ton, 2 foot long. It's important these are the same length. So basically now we got 2 3.5 ton coils in parallel, so it's a 7-ton coil. Should work much better now. Now notice on the evacuation is not going as low. That's because there's oil in there, and the oil is boiling, so you don't have to worry, you know, if you're not going super low on the vacuum. It would eventually go if you boiled all your oil out, but there's no need to do that. And I'm still going to do a triple on this circuit, which is isolated. I have it isolated up there at the valves, so I don't have to pull down the rest of the system. Alright, so we got the 2 coils in parallel, but you can see here on the thermal, the subcooling's too high. It's only using the first few loops for heat exchange, and all the rest are liquid, and we're still, head pressure's jumping up too high as it switches cycles and it's tripping on the high head. So I got to take charge out. So look at our subcooling. We got our pressures 384, 60 degrees. So we got 54 degree subcooling. And so we got an overcharge condition. So I'm just going to dump some refrigerant in the other circuit. You can see I'll bring down my head, because that's the standby circuit, not going to be used until summer. And we'll go back and check our subcooling, and also the thermal camera would show this. So the room's about 67 degrees, and the floor, you can see here, 70 degrees, 71. You can see the pipes in the floor. I got some performance data here because I've been tweaking it a little bit. So since the water's warmed up, You see how the 7 tons worth of coil, they're fully being utilized. The last row is where we're getting our subcooling and running about 15 degree subcooling. There's the outlet for the liquid. So all of the coils are being utilized because the water's warmed up. When the water was 50 degrees, when the building was cold, the heat exchange works so well that you don't end up using the whole coil. So you really got to wait till it warms up before you can see the whole coil being used. So I tried some things on capacity. We got some numbers here. So I tried putting an expansion valve outside because I knew I could get more capacity having an expansion valve on the condenser coil, and it did 4.1 tons, but I ended up tripping on high head pressure again. And the reason why is the liquid feeding out. Expansion valves hunt. This valve's not used, it's just used on the cooling cycle. But on the heating cycle, as soon as that valve closed off, they would end up backing up the refrigerant in this coil and then get a nuisance trip on the 500 pounds. So I did have to pull the expansion valve back out. And then I went to the original orifice, which is 65 thousandths, and then you do the numbers, and then as I saw, the tonnage was lower because of I got my 8.5 gallons per minute times your temperature delta across your water coil, divided by 24, 3.75 tons. So I knew I needed more feeding because this was all today, and the smaller oil orifice was pinching it off too much. So I drilled it out to 0.75, and my numbers got better. And so you can see I'm getting 4 tons with that size orifice. And then a real quick looking at the power consumption. Now this doesn't have power factor, so it's going to be a little bit off. I don't have a true watt meter. Just use my amps times my volts. 3.6 kilowatts, and that's also including the pump. And then we have our output. We're running basically 13 BTUs per watt. That's 4 times more efficient than electricity. Outside is 40 degrees right now, so this is design conditions. The room is warm. Outside is the best that the heat pump's going to do. You know, we're getting some pretty decent capacity and some decent efficiency. I was hoping to see 5 tons, but I'm not going to worry about it. And highly recommend fixed orifice, and which is what the Goodman defaulted as. Some units though have expansion valve outside. You're gonna have a hard time because you're not gonna be able to hold the refrigerant, in these water coils because they're so much smaller in volume. I definitely recommend an orifice. Expansion valve is fine for the coil itself because the condenser is much bigger. Have some ductwork here I'm gonna put up in the ceiling there. After a long job out here, there's only one thing left to do. Tiny whoop the place. Half-ounce quadcopter. I've been waiting to fly those rafters. And there's my piping. Basically run up the wall there. across the rafters. Oh, this looks cool. There's my unit. I like those HEPA air filters. There's my ductwork. Got it strengthened with some wood there. Check out the end here. Now let's have some fun. I get 3 minutes on the battery on this thing. I go about 20 miles an hour. It does get pretty brutal in the wind. There's turbulence off of the fans. Let's open her up. As soon as I got outside, the wind was very brutal, about 15 miles an hour. So it started just pushing me away there. And the video is degraded because it's going through the metal building. I usually get 1,000-foot range on this. Well, I hope you like watching the video. Thanks for watching.